Yes, you can.
Like, are we going to have any like something like study guide before the final exam, or we're just on our own?
Um, yeah, yeah. I'll post something up today for you guys. And I'm gonna hold a practice session tomorrow.
Okay,
But
perfect.
yeah, I would mainly study lab previous exams and study guides for the final. That'll be your guide mostly. But if I have something ready, I'll upload it.
Thank you.
Yeah. Okay. So we have this solid, which is a weird solid. It has a hole. I don't know. Can someone tell me what this looks like?
Washer.
It's a well. It's okay. So the cross section is a washer. Yeah. But I mean, it looks like a pot. You know, in those um, when they melt stuff, right? Those pots where when people melt stuff like very high temperature, melt it like metal, they pour it in those pots. This reminds me of that. Yeah, but I mean, there is a massive hole over here. Okay, so we want to find a volume of this solid with a hole in there. What you can really do is maybe find the volume, find the entire volume, and find a volume of this cylinder and then subtract. But that doesn't work all the time. So um, what you guys always want to do is draw the solid. Okay, if you can't draw the solid, that's all right. Make sure that you draw the region. Okay, draw this region. This was the region. And then just draw a washer. Okay, so how is that going to work? It's as if, this is how it works. It's as if I take a rectangular strip. So here is the rectangular strip. That's what we have been doing for area also. Take a rectangular strip and revolve that rectangle around the axis of revolution. This being the axis of revolution. Okay, and when you do so, it does create this washer. Okay, so if you can't draw the washer, try to at least imagine it. But I am worst at drawing things. I really am. So I don't think you guys should be worse than me when it comes to drawing a washer. Draw the washer out. So you want to know how to identify the radius. Draw the washer out here. Okay. And then identify points. Okay. Begin with the center of the washer. This is the center. And the equation for it is y equal -1, because that's what the region is revolving around. Okay, then you're going to identify the point on the inner circle of the washer. This is the inner circle. The point on it is it falls on the line y equal to 0, and also identified a general point on the outer circle of the washer. This is the outer boundary of the washer, this point, and that point falls on the graph of y equal to √x. Okay, now next thing you're gonna do is find the inner radius and the outer radius. We're gonna find the radii. Okay, so let's go with the inner radius. Here is, let me use a different color here. The inner radius, the radius of the inner circle, this is basically, whenever you're finding distance, you just always do top minus bottom. Top minus bottom. So here top is 0, and then you do minus bottom. Bottom is -1. The radius, obviously, the radius of this disk is, or this circle is 1, right? The radius of this circle is 1. 0 minus -1, that's equal to 1. Let me move this. That's equal to 1. And that's, I'm going to call that R in, R sub in. In means inner, inner radius, inner radius. Okay, and the outer radius is this distance. R sub out means outer radius. And again, you always do top minus bottom. Okay, it's intuition. If you're finding a vertical distance, you take the bigger y minus the smaller y. Okay, I mean, if you just think about it, assume that on the graph, assume that this point is, let's just say this point is 1.5. Okay, 1.5. So the distance between 1.5 and -1 is 1.5 minus -1, which would give you positive 2.5. Always do top minus bottom. Okay, so that gives us square root of x minus -1. And that's equal to square root of x plus 1. Okay, so you wonder why is the radius a function of x? It is, guys, radius is a function of x. That's because when you vary x, if I change x, the outer radius is going to change, doesn't it? See, if I choose x smaller, the outer radius gets small also. I choose x big, the outer radius also gets big. So the radius of the outer disk is a function of x. And the inner radius doesn't change. The inner radius is always 1. And that's because no matter where you are, the inner circle is constant in radius. Okay, so we have the outer radius. That's something that we need, and we have the inner radius. Okay, and we are ready to set up the volume integral. So here, basically, you're going to get the volume, you're going to do the outer volume minus the inner volume. Okay, and each of these is an integral. All right, so again, the volume is, think of this as a cylindrical shell or a cylindrical washer. Volume is pi r squared times, let me write it down. So it's pi times r squared, the big R. Okay, times the thickness, which is dx. And this is going from, it's going from 0 to 4. This, it says n x equal to 4. So this is where the washers stop. So 0 to 4, that's the outer volume. And I meant to write that in pink. Okay, minus the inner volume. That's again, integral 0 to 4 pi times the inner radius squared. Times thickness, which is dx. Okay, and since both of these integrals have the same, they have the same limit of integration, they both from 0 to 4, I can just express this as one integral, and I can even factor out the pi. Okay, so the expression for volume is equal to pi times the integral from 0 to 4 of the outside radius is square root of x plus 1 squared minus the inner radius, which is just 1 squared. Okay, integral with respect to x. Again, dx here stands for the thickness. This is dx. Thickness of the washer. I hope this makes sense. And you can easily find this integral. It's not that bad, but our main concern here is the setup of the integral. Okay? And the hardest part is really identifying the outer radius and the inner radius. And you subtract them. Square them, subtract them. That gives you the volume of the solid without that hole. Okay? Questions on this? Any questions? Yes, no.
How are you gonna word, like on a test? How are you gonna word it going like around -1?
Okay, so region bounded by the graph of y equal to root x and the x-axis and x equal to 4 revolved around x around y equal to -1. There we go.
Okay.
The problem I didn't notice I didn't write the whole thing. Okay, so next example. Let's go with the region.
Professor,
Yeah.
are we ever going to have problems where we'll need to find the area and then like take the integral of the area, or is it always going to be where I guess it's kind of given to us like it is here?
So you mean the integral of the area to find volume?
Yes.
Are you talking about solids that don't revolve? Probably.
Yeah.
Yes, that will come up. Those solids are not solids of revolution, but yeah, we'll get to those. Okay, so here the region is bounded by the graph. Let's go with the square root function probably. Give me a second. Let me see if I can find a good function. Yeah, this will be good. So graphs of y equal to root x and basically just y equal to x. Let's just make it simple. And I'm gonna revolve this region around multiple lines. Okay, I'm just gonna do parts A, B, C, and so on. Okay, so let's find the bounded region first of all. We all can graph these two functions hopefully easily. So here we go. So try to, again, picture the region before you do the graph. This is the square root, and this is y equal to x. Okay, and this is it. This is the region. All right, there is no other bounded region. And it has 2 points of intersection. So we got to find those. I didn't have that here though. I just had the graph of square root of x and just the x-axis. But here you have two graphs that are bounding the region. So please find the points of intersection. Just set them equal. And again, you can solve this by inspection. For instance, of course, 0 is going to work, right? So you plug 0 in, you get 0 equal to 0. So is 1. 1 is also going to work. Square root of 1 is equal to 1. If not, if you don't see that, just square both sides. You get x squared equal to x. And then move over to the left, set equal to 0. Factor out the x. You get x minus 1. And that gives you x equal to 0 and x equal to 1. Those are the intersection points. And the y value is just 1. Because if I plug in 1 into either of these, I'll get 1. Okay, so just the algebra here is, if the algebra is simple, please don't spend too much time on it. And again, you can always solve by inspection. So those are the intersection points. And here I have the graph of y equal to x. And the graph of root x. Root x looks something like that. And that's pretty much it. Again, this is our bounded region. Make the graphs, make the region as big as you can on paper. Please don't try to save space. When you do math, you don't want to save space, okay? You want to take as much space as you can and be as neat as you can. Okay, so now we are gonna do a bunch of questions. Part A, let's just revolve around y equal to 0. Okay, so we're just talking about the x-axis here. And I'm gonna copy and paste this. See, this is a good thing, great thing about doing stuff on a tablet, because you can just copy stuff and paste. You don't have to redraw. Okay, so this is the axis of revolution. Equation is y equal to 0. I label things, guys. I always label things. All right. So as this goes around, you can draw the solid if you want. Draw the solid if you want. So if I were to draw the solid, it looks something like that. Okay, it's again, it's like a ball. It's a ball, but inside of it is kind of straight. You see that? It looks like the Pac-Man. Yeah, Pac-Man with the eye here. You can also use that GeoGebra to graph these if you want. But again, this is going around. What I want to draw is not the solid. Don't spend time on the artsy stuff. If you have a hard time drawing three-dimensional things, don't. But at least draw the washer. Okay, so how's the washer created? The washer is created by taking, again, a rectangular strip like that and revolving it around. So when this goes around, this washer is created. This washer is just a slice of the solid, okay? And it has some thickness, but again, it is just a slice. And all you care about is that slice, okay? Because it gives you the outer radius and the inner radius. All right, so if you want, again, you can draw the washer out here. You don't have to because you already have it. Okay, and what you want to do is, see, I am spending too much time on this. Okay, so what we want to do is identify inner and outer radius. So make sure that you label things. Here is the center of the washer. Center of this washer is y equal to 0. Okay, this point on the washer falls on the green line. That point is y equal to x. Okay, so that's a point on the inner circle, and the point on the outer circle, this point falls on the graph of y equal to root x. Okay, so we can easily find those radii. All right, so yeah, so let's do it. The inner radius, oh, come on, R in is equal to top minus bottom, x minus 0, always. Okay, so the bigger y minus the smaller y. And then the outside radius is going to be, this is the outside radius. That's equal to top minus bottom. Top y is root x, bottom y is 0. So root x minus 0. Okay, and we need both of those. We need that and that to find ourselves the volume. So set up now the volume integral. Volume is the integral from 0 to what, guys? From 0 to what?
1, right?
1. Yes, this region here, it stops at 1. Or you could say that these washers range from 0 all the way, to 1. Okay, the solid is you stacking up all those washers. So stack up means you take the integral from 0 to 1. Leave the pi out, please. Pi out. So you do the bigger radius. We are finding the volume of the outer, the entire solid. Okay, so you do pi times the outer radius. The outer radius again is square root of x minus 0. You can just drop the 0 squared. Okay, minus because we are taking out the inner solid, minus the inner radius squared. So that's just x minus 0. Okay, that's the volume integral. And again, the entire purpose here is just to know how to find volume. That integral gives you the volume. All right. And again, on the exam, for most of the problems, I just ask you to leave the answer in integral form. I might ask you a question, maybe a question or two where you have to finish the problem, but 90% of them just leave. So I left it. Look, I left the 0 here. You can just drop it. You can just drop this. But I left it just in case the the axis of revolution is not 0. If the axis of revolution was instead y equal to -1, you do exactly the same thing. Okay, so the inner radius is going to be x minus -1. And the outer radius will be x square root of x minus -1. Just like the last problem. Does that make sense?
What did you call the outer radius?
What did I call it? What do you mean? R
Okay.
out, you mean? This?
Is it R out?
Yeah, R
Okay.
out. Okay. You can use a capital R for the outer radius and little r for the inner radius if you want. It's up to you. You don't even have to call them anything. R-O-R-I.
So we won't have to solve for how many units it is for any of them?
Yeah, for 90% of them on the test, I'll just ask you to leave it. Unless it's an interesting problem, like the volume of a sphere that I found. I might ask you a question like this one where you have to find the volume. But for most of them, you're just gonna, I will tell you, leave the answer in integral form. Okay? Yeah, I'll be telling you, leave the answer in integral form for 90% of these problems. Okay, so let's revolve around something else. Let me copy that thing. Okay. So part B, same function, same region, revolve the region around, let's make it interesting, y equal to, maybe y equal to 1. Yeah. Not y equal to 0, but y equal to 1. So here is the region, the graph. Let me extend the y-axis right there. So now this is our axis of revolution. God, man, if you don't know what the line y equal to 1 is, there. Okay, that's the axis of revolution. We're gonna be revolving around that. Okay, so again, guys, don't think too much. Don't. All right, please don't. That's not math is all about. It's not about you thinking so much, really. Like with calculus 1 and 2, it's not like that. You just do it. Okay, so you do as I teach you. Take a strip like that and revolve that strip around. When it goes around, it creates a washer again, just like that. Okay, and what you want to do next is draw that washer out. Let me draw that out here. Here is the inner circle. That's the surface of the washer, and this is, again, the thickness of the washer, whose measure is delta x. Okay, that's dx. All right, and we are ready to identify the outer and the inner radius. Okay, so begin with the center always. The center of the washer is at no-brainer. It's at y equal to 1. The axis of revolution is always center of the washer. So label, okay? I want you guys to show the process. Don't just set up the integral. Don't just write down the answer. That's not going to tell me anything. Okay, I need to see your thought process. If you just write the integral down and say, oh, I did my work on scratch paper, and your integral is wrong, I have no idea what you were thinking. But if you do write stuff down, then you should get a lot of partial credit, even though your integral is wrong. So anyway, that's that. Now let's take points on the washer. So you might say, hey, am I gonna take that point? This point? No. Take a point on the washer that falls on the graph. Okay, so look at that. Look at this rectangular strip. Look at that strip. That strip is here, okay? There is a strip. So take points on that strip, just like the way we've done over here. I took my rectangle strip right there. Again, here's that strip. And I took points on the strip. The strip gives you points on the outer circle and the inner circle. Same thing over here. Here's a strip. We have, for the outer circle, this point. This is the outer circle. That point falls on the green line. So the equation is y equal to x. Okay, and then the inner circle right there, the point on the inner circle falls on the graph of square roots. Okay, and now we are ready to find outer radius and the inner radius. Let's go with the outer radius. Radius, by definition, is the distance from center to the point on the circle. So we are talking about this distance. That's the outer radius. And it's again top minus bottom. Top minus bottom. 1 minus x. Always, guys, the bigger y minus the smaller y. Okay, and the inner radius, which is the distance from the center to the point on the inner circle. Okay, so that's again top minus bottom. Bottom is root x. The difference between those two. Okay, yeah. If you do root x minus 1, if you were to change the order of these, then the quantity is going to be negative. And that makes absolutely no sense. You don't want a negative radius. Radius has to be positive. Same goes for this one. Like if I do x minus 1, well, obviously here your x's are smaller than 1. The line is below 1. That would have given you a negative radius, and that's nonsense. Okay, so by now volume is again pi, factor it out, integral from 0 to 1. Okay, the inner radius, the outer radius squared, which is 1 minus x squared minus, so we are doing the outer volume minus the inner volume minus the inner radius squared, 1 minus root x. There you go. That's your volume integral. Outer volume minus the inner volume expressed as one integral. Okay? Now, in theory, in calculation, when you're doing calculation, to be honest with you, it wouldn't matter if you, by mistake, if you write x minus 1 over here. If you wrote your radius the opposite of what it should be, you still, in the end, the integral, although your integral is not a good representation of measure, it is going to give you the right answer because of the square. You're squaring this thing anyway. So if this is a negative, it squares out to become a positive. The square of negative r and the square of r are the same thing. Okay, but I want you to do it the right way, okay? Give the right representation of things, of measures, please. Any questions about this? All right then. I hope it's easy enough. I really hope so. Okay, so that's it, I guess, with revolving around horizontal lines. Let's now revolve a vertical line. That's when things get effed up. So see, let's revolve the region R around the y-axis. Not the x-axis, but the y-axis, which would be x equal to 0. The equation of the y-axis is x equal to 0. So things are not going to work out the way they did here, okay? Because when this goes around x equal to 0, then the solid, this is what the solid is going to look like. Okay, just three-dimensional. Your washers are going to be horizontal. Okay, washers, when revolved around the horizontal axis, the washers are vertical. And it makes perfect sense that the washers here are horizontal, right? They are horizontal. So you'll be taking a strip like that and revolving that strip around. Let's do that again. With a hole. That's what it looks like. Okay, so imagine I have this, I take a semicircle like that and revolving that around the y-axis, it creates a sphere. Okay, to find its volume, instead of slicing it up vertically, I slice it horizontally. Okay, I take horizontal slices like that. Okay, so that's what we are doing here. And if you want to find the volume of the sphere like that, you can just find the volume of each of these cylindrical discs and add them all up, do an integral. That's what we are doing here. Okay, the thing here is, guys, first of all, two things to notice. Integration is no longer with respect to x. It's with respect to y, because the thickness of this washer is a small change in y. This is the y-axis. Let me clean this up a little bit.
Professor,
Yeah.
Why it revolves around x equals 0? It has hole.
It has what?
It has hole. It has a hole.
Well, what else is it gonna do? I mean, don't you see that there is an empty space here? You see this empty space? Look, let me draw the solid for you. I'll draw the solid. So when this is revolve around, almost. Just do that one more time. I think there's a way that you can copy, paste, reflect. But whatever. So it's, I mean, the solid, it has all this empty space. This is the region. Look, this is the region that I'm revolving. Okay, I'm not revolving this region. I'm revolving this region. So when it goes around, you have all of this empty space. This is empty.
Oh, thank you.
Yeah, so when you take a washer, it does have a hole right there. Yeah. So as I was saying, the thickness of this washer is now dy. That thing looks like an eye. So let me just dy. All right. And since our washer is horizontal, to find the radius is gonna be the difference between two x values. Guys, I hope you're listening. Difference between two x values. That's how you get a horizontal measure. Okay, again, before our washer is vertical, these are y values. You all see that? Those are y's. Top y minus the bottom y. Here it's gonna be x's. For instance, this point is from here to here, and that's an x value. This point is from here to here. That is an x value. Okay? The center, for God's sake, the center is at x equal to 0. So it makes sense that we have to express our equations, our functions, as a function of y. You have to solve for x. So that's a big deal. You gotta make sure you understand that. Since, I'll write it down. Since washers are horizontal, their radii, or I should say the radius, is the difference between two x values. Let me highlight that. X values. Okay, so we have to solve each relation for x. Okay, we're talking about the relation that describes the bounds. Y equal to root x, y equal to x. for x in terms of y. Okay, so again, this is consistent with dy. You want to express your integral in terms of y. Why is that? Because thickness is dy. We're going to be doing integral with respect to y. Okay, so we have our bounds. This is y equal to x, or x equal to y. This is already solved for you. If y is equal to x, then x is equal to y. Okay, but so this is what we're going to do. Y equal to x. I don't need to do anything. X is equal to y. So I'm going to write that as x equal to y. And then we have the square root, y equal to square root of x. Square both sides, you get x equal to y squared. Okay, so I'm going to re-express that relation in terms of y. X is y squared. So look at this. I have things that help me find the radius. I have x equal to 0, x equal to y, x equal to y squared. Those can be used to find horizontal distances. All right, so next, draw the washer out. Okay, and label things, starting with the center. Center is at x equal to 0. Before it was y equal to something, now it's x equal to something. Okay, this is my strip, the rectangular strip that we took, this strip right here. The point on the outer disk, this point, this, it falls on the green function whose equation is x equal to y. And the point on the inner disk or the inner circle, it falls on the blue function, this point. It's on x equal to y squared. Okay, so we are ready to find the outer and the inner radius. Okay, let's go with the outer radius, or let's go with whatever. Let's go with the inner radius. This is the inner radius of the washer, and it's who wants to go? How do I find that inner radius? Anybody?
Right minus left.
Yes, right minus left. Bigger x minus the smaller x. Okay, the bigger x is this function. It's y squared. Okay, minus the smaller x is 0. Okay, so that's the inner radius. And then the outer radius, same thing, bigger x, this distance, which tells you that x is equal to y. Bigger x here is described by y, minus the, again, minus the smaller, which is 0. So again, if the axis of revolution was somewhere else, like imagine the axis of revolution was at -1, then you would have done minus -1. You know, this is the center of revolution. Okay, so we have our R out, R in. Now we are ready to set up the integral. So what you do again is you take the volume of the bigger solid minus the, or the volume of the outer solid minus the volume of the inner solid. Okay, so again, there's a pi I'm gonna be taking out. And don't forget, guys, the thickness here is dy right there. It's an integral. Let me just write down the integrand. So the outer radius again is y. I'm gonna write down the minus 0 anyway. Y minus 0 squared. Always minus, take out the inner volume, which in this case is y squared minus 0 squared. Okay, those squares is because of the pi r squared. And then we multiply this by dy to get the volume of this cylindrical washer. Okay, put a dy here. So this obviously is integral with respect to y. Let's see what that means. It means that if I want to again find the volume of the solid, I am going to add up the volume of all of these washers. Okay, and let's do that again. So we have infinitely many washers stacked up like that. These washers go from y equal to 0, and they end at this y where y here is 1. This point is 1, 1. So this integration is also ranging from 0 to 1 for y. But these are y values, guys. This is y starting at 0 and ending with y at 1. Any questions? Questions? Okay, so let's see what to do. So again, if I were revolving around a different vertical axis, imagine this is a 1. So it would be around that. You get the inverse Pac-Man, like upside down Pac-Man. If you're going around that axis, then I mean, all you gotta do is just find the inner outer radius. Really. If this was, let's say, x equal to -1, this would have been, these zeros would become -1. This is x equal to -1. You know, just set up. Here is the thing, guys. I'm gonna do a lot more of these, by the way. But here is the thing. We don't like something about these problems, this type of problem. When it's when you have a when your function is a function of x. So again, originally in the problem, functions are functions of x. You have y equal to root x. Well, not bad. Y equal to x. If the functions are functions of x, we wouldn't like this part of the problem. Well, for this problem, it was very easy to solve each of these equations for x. All you had to do here is square to get x in terms of y. But in 99.999, almost 100% of cases, solving for x is a pain in the neck. It's really hard. Imagine for a moment that your function here was, say, x squared plus 2x, you know? Or if it was a square root of x plus 2x, and you had to solve the equation for x. Imagine if this is like a sine x. Then you would have to do a sine inverse to solve for x. The algebra is obnoxious in almost all cases. So is there a remedy to that? We just don't want to do integration with respect to y because that requires us to solve, to express these in terms of y. When you use the washer method, the washer is horizontal. Okay, so those radius, the radii are the difference between two x values. That's why we had to solve for x. Whenever someone asks you to solve for something, you have an equation, solve for x, expect a lot of difficulties. The most difficult, one of the most difficult things in algebra, solve the equation. There's actually a guy on YouTube. He loves solving equations. I've been kind of like getting addicted to his videos. The equations he comes up with are dumb as hell. Like they have no application in reality. They're just, ugh. But he comes up with these methods. It's really cool. If I find the videos, I'll send them to you. It's useless. It's useless to watch those videos, but kind of addictive. But no one likes solving equations, okay? So is there a different method that we can use to find volume? Yes. It's called the shell method. So let me start a new notebook. So this is called volume. Again, solids of revolution. Shell method, not washer or disk. And it's section 5.2, I think, or 5.3. Yeah, 5.3. Let me see if I can quickly find a GeoGebra. Yes. Holy crap, this is really cool. Okay, I gotta figure this out. Give me a second. We'll just figure it out ourselves together. Hold on, let me share my screen. Looks crazy. This is a really cool solid though. The equation is sin x plus x to something better. Stop. So let's go with x squared. I can't even see the solid here, man. All right, give me a second. Okay. So it's, I believe, let me get rid of these. Let me reset. Let me reset that again. So slow. Oh, this doesn't give me the option to revolve things. Okay. Yeah, whatever. No, this thing sucks. Okay, it sucks. But so here's what we do, or what happens. Let me just draw it, and then I'll come back to this animation. Give me a second. This doesn't give me as much freedom as the last. I think same guy wrote this program. Give me a second. Let me switch. It's easier if I begin by explaining myself on my own. So let's say we have some function, and how are functions typically given to you? Y equal to f of x, right? Y equal to f of x is a typical function. And let's say here is the graph of y equal to f of x. And let's say this is the region. It goes from A to B, like that. Okay, and yeah, so here is our region. And this region is revolved around, let's go with just the y-axis, okay? So this is the axis of revolution. And as we saw that if I were to take washer methods, if I were to use the washer method, then I would have to get the radius, I would have to have x equal to something, because horizontal means that you have to find your distances horizontally. You have to have x. Okay, so let's say that this revolves around. Let me see if I can draw. This is after it being revolved. I'm just trying to give this a sense of 3D right there. Okay, so we have the solid, and yeah, there's a hole right there, whatever. Instead of taking a horizontal strip and letting it go around, so if I were to take a horizontal strip, as it goes around, again, it creates that washer. I don't want that. I don't like the washer method, let's just say. So I like to do integrations. Again, the washer, because of that thickness being dy, it requires integration with respect to y. I don't want to do that because I have f of x here. I want integration with respect to x because f of x. So what I will do is I take a vertical strip. Here is that vertical strip. Why is a vertical strip good? Because the thickness of that strip is dx, isn't it? That thickness is dx. So as the region goes around, imagine this vertical strip goes around, it definitely doesn't create a washer. It creates a cylindrical shell. A cylindrical shell. I hope you guys can imagine or picture that in your mind. It is a cylinder. It's a cylindrical shell. And our goal here is to find the volume of that cylindrical shell and do an integration, because the solid basically consists of infinitely many of these cylindrical shells. I have another cylindrical shell here. I have another here, and so on. Okay, just like an onion, kind of, it has shells. You could do that with the solid. Okay, so question is, how do I find the volume of this shell? Well, let's draw that shell out. Definitely not filled. Yeah, and this has some thickness. All right, so that's our shell. I want to find a volume. This is dx. All right, now the volume of this shell depends on two things. It depends on its height and the radius. Okay, so look, this point, which is on the shell, it consists of x and a y. The x value of that point is just x. Okay, because why is that? Because the distance from here to here is x. Guys, that distance is x. And the y value, because it's on this graph, the y value is just f of x. Okay, so I'm taking a point on the strip as I have done for the rest of the problems. Okay, so we can say that this height, the height of the shell, this height is the same as the y value, which is f of x. Okay, and the radius is, look at that, this is x equal to 0. And yeah, from here to here again is x. So this radius here is just x. Okay, please let me know if you didn't get that. So again, if I take any random point here on the graph, the x coordinate is x and its y coordinate is f of x. Therefore, again, that horizontal distance is just an x value. From here to here is just x. Okay, so I have the radius, the height, and the thickness. How do I find the volume of this cylindrical shell? Well, this is not a cylinder, it's a shell. Okay, let me show you. I will activate my camera and I'll show you. Give me a second.
This thing is hollow, right?
It's what? Yeah, definitely.
Hollow?
It's hollow. It is hollow for sure. Guess what I'm looking for? I am looking for just a piece of paper. Okay, this is good. Let me show you, man. So, guys, this is a shell. This is what we are looking at, a cylindrical shell, not a cylinder. It's hollow, as Nate just said. It is a shell. That's what we took, okay? So how do you find a volume? Again, the shell has some thickness. It's really, really small. Okay, but if you want to find the volume of the shell, you open it up. It becomes the surface becomes a rectangle. Okay, I'm not going to show you the label because it has my address and everything on it. Actually, who cares here? Yeah.
So it's kind of like finding the perimeter or the area of the perimeter, right?
Area of the
The perimeter. for the shell, it's like finding the area of the perimeter for it, like
You mean area
the-
of the rectangle? Area of the
Yeah,
rectangle. Yes. Yeah. So you open it up, it becomes a rectangle. We are finding the volume of this rectangular box. Why volume? Because again, there's still a thickness. We have a little bit of a thickness over here. So cut it open. Open it up. We get so I'm drawing it like that because of the thickness. Very tiny thickness. Okay, so now the width of this rectangular box is the same as the altitude of the cylinder, right? And we can see that. If I open this up, the height of the cylinder is the same as the width of the box. And the width of the box is f of x. All right, so that the dimension here is f of x or y. And then the length, Alexa, stop. The length of the rectangle is the same as the circumference of this circle. Circumference of the circle becomes length of the rectangle, and that circumference is 2 pi. 2 pi times radius, and the radius here is x. So again, this here is circumference of the circle. Yeah, so again, this circle's circumference is the same as this length. And I could use a color here if you want. Let me draw that in orange. And it has some thickness. So there. That's that. And then the thickness of the box is just dx, okay? So how do you find the volume of this box? dv, we just take length times width times height. Length times width times thickness. Okay, length here is 2 pi x. Maybe I should just write all that in orange. Width is f of x, and thickness here is just dx. Okay, so this gives us dv. And of course, we do, again, dv means just an increment of volume. It's just the volume of the cylindrical shell. To find the total volume, just do the integral. Okay, look at the solid. The solid consists of stacking up all of these shells. There's a shell right there. There's a shell right here. There's a shell here. Another shell here. It goes, these shells begin with A and at B. So just do the integral from A to B. That's the Riemann sum. And you can take 2 pi out because it's a constant multiple. So 2 pi, the integral from A to B of x times f of x dx. So this is the derivation of the volume for this for the specific example. But again, on the exam, I want you to kind of derive this on your own every time. Okay. I'll show you how to do problems. But any questions before we take a break? So again, 2 pi times the distance, the horizontal distance, vertical distance, pretty much. Okay, let's do 15 minutes. All right, great. So same problem, guys. And we are gonna revolve this around again, y equal to 0. So find volume. Revolve around y equal to 0. And here we're going to use shell method instead of the washer method. Because again, the washer method, when a region goes around a vertical line, washer method will be dy. So again, make sure you guys understand that so you don't get confused when to do what. So a vertical line, there's the axis of revolution here is vertical. If I take a horizontal strip, go around to get a washer, this will be a dy. Integration will be with respect to y. Okay, so to use the shell method, take a vertical strip like that. So this is gonna be dx. The thickness is dx. Let that shell go around. Draw the shell. Again, guys, you don't need to draw the whole solid. We just draw the shell. Roughly draw the shell. Okay, copy that shell out because we are going to identify the dimensions here. Be patient. Be patient. When I tell you be patient with these problems, I mean it, because the good news is that you're not going to evaluate the integral. You're just setting up the integral. So don't rush through the problem because you're not doing basically 90% of the problem, which is the calculation, solving the integral. Okay, so here's our cylindrical shell. And you know what? There is like I should also try to draw that because of the thickness, right? So this is the thickness of that cylindrical shell. Okay, that's our delta or dx. There. All right. So what we do is we are now going to identify the height of this shell. Okay. This is the vertical strip that we took. It's right here. That is the vertical strip. Okay. There are 2 points on this vertical strip. We have this point, which falls on the graph of y equal to root x. Okay, so we're talking about that point. And this point, it falls on the green graph. So here y is just x. All right. That's that. We also want to identify the radius of the shell. So again, the center here is the axis of revolution, the equation here is just x equal to 0. That was the axis of revolution. Okay, so from here to here is, guys, what is that? Anybody? That's,
It's X.
it's
It's
just,
four.
huh?
It was one, something like that.
No, why would it be 1?
Oh no.
This shell varies. There are infinitely many shells. So as you vary x, those shells are varying too. But the distance from here to here is, look at that, it's x, right? This is x. Since this point is x f of x, the horizontal distance from the axis of revolution to the point on this strip is just x. And I drew that in orange, I guess. Yeah, x. Or x minus 0. So why is that? Because again, if you look at that strip, this point is, that point is x, f of x. And this point here is x. Actually, instead of f of x, we actually have a expression for that. The expression here is square root of x. Okay, and for this point, the coordinates are x, and y value is also x. Happens to be x here also, because it's on the green line. Okay, so the horizontal distance here is just x. X is not a constant, x is varying. Everything here varies, guys. When you move, when you look at a different x, you get a different shell. So both the radius and the height of the shell change as you vary x. Anyway, that's the radius of the base, okay? Because the horizontal distance is x. And you could again think of it as x minus 0. Because the center is 0. This x is equal to 0. So you take the value of this x, which is just x, minus 0, or just x. Okay, so now we are able to get the height of the shell. The height of the shell is always top y minus the bottom y. That's square root of x minus x. That gives you the height of the shell. That's the height. We have the radius, and that's all you need to set up the integral. Okay, so the integral volume is equal to pi, 2 pi, times the radius, which is just x, or x minus 0. And that, by the way, that goes in the integral. So 2 pi x, again, the 2 pi x is the circumference of the shell, times by the height. And the height is root x minus x. And it's integration with respect to x. And well, the Riemann sum goes from 0 to 1. These strips, these vertical strips begin at 0 and they go up to 1. My x here varies from 0 to 1. Those are the limits of integration. That's it. That's a volume integral. So you be the judge of that. Which integral is easier to evaluate? This one, or let me see, going back. So same problem that we did using the shell method right here. I don't know, both integrals look equally bad. So this is the volume when you want to do dy washer method. And this is volume using the shell method. Both of these integrals give you the same value. If you do these integrals, have the patience to do them, you should get the same thing. But the good or the advantage of using the shell method here is that I don't need to convert these into x as a function of y, just kept it. Integration is with respect to x. Great thing about shell methods. So let's take this region and now revolve it around a different axis. Okay, so this is A. Let's do B. So revolve the region R around another vertical axis, y equal to -1. That's not y, I'm sorry, x equal to -1. Actually, hold on a second. Did I do a, no, I didn't. Yeah, so again, using shell method. Okay, so again, here is the region. That's y equal to root x. And the axis of revolution is x equal -1. Going around that. So again, guys, you don't need to draw the whole solid. Just draw the washer, the shell. You don't even need to draw the whole shell. You can just draw half of the shell. If the shell is just taking too much space, I could just draw half of it. I could just draw this part of the shell. That's sufficient. That will give me the height, the radius, you know. But again, if I wanted to do washer method, I would have to take a horizontal strip, let that go around, that goes around, that creates a washer like that. But again, this is a dy, so you would have to change these to, or solve these for x. Okay, but using shell method, again, take a vertical strip like that. Why do we take a vertical strip? Because of the dx. It's just convenient. Okay, so again, you don't need to draw the whole shell. Draw half of the shell. See, that's just half of the shell that I am focusing on. I mean, that this is good enough for me to kind of understand what the radius and the height are. Let me draw that out here. Again, this thing again has a thickness. That's the thickness of the shell. That's your delta. Uh-oh, the whole thing just vanished. Okay, let's do that again. You can make it a full shell if you want. I'm just since the whole thing is just too big, I don't know if I have enough space. So There. Okay, again, here is the axis of revolution, and please label it. Always label the axis of revolution in your picture. X equal to -1. X equal to -1. It's an X value. Okay, so we need two things. I need the height of the shell. So same, guys, same as before. This point here is, x, f of x, which is square root of x. This point here is x because it's on the line where the equation is x. You could just write down the y value for it. Okay, write down the y value here. I'll just do that too. So here y is root x, and here y is just x. So just like before, the height of the shell is not changing at all, right? This shell is the same as this shell in height. Height is the same. It's the radius that has changed now, you know? So that height, again, is the top y, the blue function minus the bottom y, which is the green function. That's x, height. Now let's find the radius. Okay, so radius, guys, is always right minus left. Height is top minus bottom, radius right minus left. So if you could see that from here, if this distance is x, and this distance is 1, everyone listen, please. Then the whole radius is just x plus 1. One more time, from here to here is x, from here to here is 1. Therefore, the radius is x plus 1. Or you could just use the same idea, right minus left. Just take the right x value is just x minus the left x value, and that thing is 1. And again, I wrote that in orange. Okay, so right minus left. Left is -1. And that gives us, again, x plus 1 as the radius. All right, so guys, remember that we call this distance x. This distance is f of x. Therefore, you got that x here, and you got an extra 1. Put that all together, x plus 1, or again, you could think of it as the right x minus the left x, which is -1. Okay, so again, I need these two quantities. I need that quantity here, and I need this quantity to set up the volume. We got the 2 pi times the integral. Radius is x plus 1. And the height is, just like before, root x minus x. Dx. And again, these strips or the shells vary from 0 to x of 1. Okay, so this is the representation of volume. All right. I have a handout here for you guys. Let me see. Is this a good handout? I have another one also. I have another one. I'll send both of them to you, but I like the problems on this handout better. So here is the type of question I would give you. I did not PDF this, guys, but let me show it to you. I'll show you the questions. I don't know. I can't find a PDF. If I find a PDF, I'll send it to you, or I'll PDF it and I'll send it to you. But here is the type of questions you would be asked. You are going to be given a region. Okay, so look at this problem. This says, let R be the region bounded by this graph, blah, blah. They give you the bounds. For each problem, set up a definite integral that represents each of the following quantities. Okay, so you have the region. Hold on, guys. Sorry, guys. Just got news my other kid is getting discharged today. Who? All right, I am now excited. Okay, so getting back to this. Yeah, you get the region, you get the bounds for the region, and you're gonna be asked to do a bunch of stuff. And again, it's just setting up the integral. You don't have to do the calculations. So for instance, you'll be asked to find the area of the region, both with respect to X and Y, volume when it's revolved around a bunch of axes. So let's do a couple of these. I'm gonna copy the problem. I'm not gonna do the area, I'll be doing the volume. Okay, so we have a region here is bounded by graphs of y equal square root of 3 minus x. We have y equal to x minus 1 and y equal to 0. Okay, so this is our region. Yeah, most important thing, you got to draw the region and you got to make sure that you draw it correctly. Okay, because if you don't, you won't know where they intersect. You won't know where the bounds of integration are. You don't know which is the top function, which is the bottom function, which is the right function, which is the left function. All of that really matters, okay? So what we want to do is find the intersection points. Okay, again, let's try to imagine or picture this graph. Graph of y equal to root 3 minus x. This is a square root graph, but it's shifted. Okay, first of all, it's a minus x. Minus x, it means that it's gonna look like that. Okay, square root of x, this is square root of x, it's opening right. Square root of negative x, it has an opposite domain. It opens to the left. And it's shifted 3 units. So the x-intercept here is going to be at 3. It's going to look like that. That's the graph of the square root. And then y equal to x minus 1 is this graph. Okay, so this is, and also you have y equal to 0. Y equal to 0 is this line. And let's just assume it's in the first quadrant. Yeah, is that y equal to 0? Yes. So I'll write down in quadrant 1. Okay, so let's find the points of intersection. Set the two functions equal. Okay, and you can solve this equation by squaring both sides, right? Or try and solve by inspection. Can anybody tell me what the solution is by inspection? Just plug in a bunch of numbers. If I plug 0, it's not going to work. Plug 1, it's not going to work. Plug 2. 3 minus 2 is 1. 2 minus 1, 1. That works. So the solution is x equal to 2. Okay, and y, just put 2 into either of these, you get 1 for y, obviously. So that's the point of intersection, POI, point of intersection. And now let's graph. Okay, so 2, 1. And yeah, again, guys, this graph, it's a square root. It's shifted to the right by 3, and it's opening to the left. So this is the figure. And the line, we all know how to graph this. So again, this point is also on the line. To pick another point, you could just plug 1 for x. If you plug 1, you get 0. This point is also on the graph. Here's your line. Okay, so there seems to be, let me see. Yeah, guys, I don't even need this information. I don't, do I? No. Here it is. This is the region. Okay? A region that's bounded, it's bounded by, yeah, so Berkhan, you're absolutely right. Berkhan, x equal to -1 is definitely a solution, but we are interested in basically quadrant 1. I mean, I'm just going to keep that in quadrant 1. So actually, let me, yeah, I don't need the quadrant. I don't need to say that. Yeah, so basically, all 3 graphs here are bounding the region, right? I mean, this can't be the region over here. You can't say this is the region because here the region goes forever. There is no bound. The problem is not telling you that the y-axis is also a bound. So this is it. Hold on, guys. All right, so let me shade.
Sorry, I'm not sure about that.
All right, so what's the issue with this region? If this region is revolved around, let's just think about it for a second. If you're like, let's say finding area, the region area is not always going to have a consistent top and bottom. We did discuss that yesterday. So for instance, if I take a rectangular strip like that, the top is green, bottom is the x-axis. Whereas if I take a strip right here, top is blue, bottom is the x-axis, right? So rectangular strips don't always have a consistent height. Just keep that in mind. So integration, for instance, integration with respect to x would be kind of complicated because of the inconsistency. See, this is your dx. Not all strips are consistent. So in practice, you do want to avoid integration with respect to x. If we do integration with respect to y, if I take my strips horizontally like that, left and right are always consistent. No matter where I draw a strip, right is always the blue graph, left is always the green graph. So integration with respect to y seems more plausible. It seems easier. Okay, but it all depends on what the question is asking us. So question here, we're gonna find the volume. Question A, find volume when R is revolved around y equal to -1. Okay, and I'm gonna do both methods. I'll do both shell and washer method. And you'll be the judge of it. Okay, so let's go with the washer. Let me see which is better. So y equal to -1 is this line. Again, be patient. That's the axis of revolution. All right, that's not a G, that's the rotation sign. Okay, so as it's going around this line, and I want to find a volume, well, if I take a horizontal, look, if I take a vertical strip like that, if I revolve that around, what is that gonna create, guys? If I revolve it around y equal to -1, what is that gonna create? A shell or a washer?
Washer.
It's a washer. So let's just do it. Here we go. There is the strip. It goes around and it creates our washer. You can, again, you could draw half washer or the full washer. It doesn't really matter, but here is the full washer. Okay. So the thing is, again, that if you're gonna find the dimensions of this washer, the dimensions is not consistent throughout the region. It's not. Because here the outer radius is determined by the green graph. Okay, whereas if I draw another strip right there, the strip here, the outer radius is determined by the blue graph. You see, you have to do two integrals here. We have to do two washers, two integrals. So the washer method is not so, it's not really nice at all, but we'll do it anyway. Let's do it. So again, let's go from 1 to 2. We have these washers, and then from 2 to 3, we have different kind of washers. So let's go with from 1 to 2. I'm gonna graph that washer out here. So this was, again, that strip that we took. All right, We are talking about this washer. Okay, locate the center. Here's the center, y equal to -1. Okay, again, the outer disk or the outer circle, this point falls on the green graph. That's on y equal to x. Okay, and the inner disk, this inner, it falls on the x-axis. This point is on the x-axis, which is x equal to 0. Oh, I'm sorry, y equal to 0, not x. Okay, so we can find the outer radius and the inner radius. The outer radius, it's equal to top minus bottom. So x minus -1, that gives us just x plus 1. Okay, and the inner radius, no brainer. The inner radius is just 1. 0 minus -1, that's just 1. Okay, so we have enough to calculate the volume of the solid from 1 to 2. Okay, let's also look at what's happening from 2 to 3 throughout this region where washers are different. Okay, so I'll be drawing this washer, the next one. Okay, so for this washer, center is still at -1, y equal to -1. Okay, but the top point on the outer disk, outer circle, that point is on the blue graph where y is equal to square root of x. Okay, and again, same thing here. The inner disk, the inner circle contains y equal to 0. This is on y equal to 0. So now we can find the outer. That's equal to square root of x minus -1. Or just square root of x plus 1. Okay, so that's the outer r. The inner r is still the same as before. That's equal to 1. Okay, so now we are ready to set up the integral, and the integral is anything but easy to solve because we just have so much going on. Yeah.
Professor, did you change the y? Because I think it was y equal square root of 3.
Was it? Yeah, I totally, yeah, you're right. These are my functions. My brain is still stuck in that last problem. See, this happens exactly when you don't label things. Remember how I said I should label things? That's y equal to square root of 3 minus x, and this, and no one is saying anything, huh? I wonder if you guys are here at all. I'm just probably just talking to myself here, huh? So yeah, that's x minus 1. So that's, let me correct that. That's x minus 1. Okay, minus 1, minus -1. Right, top minus the bottom. So that gives you just, thankfully, x. Oh, that's good news. Okay, and the inner, that should have been a square root of 3 minus x. Let me fix that. So top 3 minus x minus -1. That takes us to square root of 3 minus x plus 1. Okay, so let's set up the integrals. Let's go with the integral for these washers for this region. That region goes from 1 to 2. So volume is equal to, and again, I can take the pi out. It's pi r squared, remember. Integral from 1 to 2 for that region. We are talking about this washer. The outer radius is just x. So x squared minus the inner radius squared. R out squared minus r in squared, which is just 1. The inner radius is 1. Maybe if I color these differently. So that comes from there. And let's do a different color here. Let's just do 1 in red. Dx. Okay, so that takes care of the volume of the solid from 1 to 2, and then the solid goes from also 2 to 3. From 2 to 3, we have this washer. So plus pi times the integral from 2 to 3. And again, this is the outer radius. Let me change the color to that. Let's go with gray. Okay, so square root of 3 minus x plus 1. That's the outer radius, guys. We need to square that radius. Take away the inner volume, and the inner volume is radius of the inner radius squared. So this is a heck of an integral, okay? It's a lot of integrals, so many. So much calculation to do, so much. I mean, yeah, this integral is not that bad, but this one, oh man, you gotta square this thing out, and then you have to do a substitution rule. No one wants to do that. No one. So guess what? The washer method is just not good. I mean, it works. If you have a software, you can just calculate this integral in a second. But setting up the integral itself was a pain in the neck. It was a lot of work. I had to do it twice, from 1 to 2 and then from 2 to 3 because of that inconsistency. Okay, so let's redo the same, let's redo the problem, but we're gonna use the shell method, okay? We'll do the shell method.
I have a question.
Yeah, Angel.
So whenever we have like something like really difficult, like the one that you just showed us, we could do it to respect to dy, but in order to like avoid the dy, because it's also messy, we do the shell method.
Right.
But the shell method is still to dx.
Give me 1 second. Let me write that here. So this is using the washer method. Okay, so what were you saying?
So the first method, it was respect to dx, but that was really difficult.
What we just did, right?
Yeah. Well,
Yeah.
you know, it kind of looks difficult. So then in order to do that, we should try doing it to dy, but dy is also difficult.
It's
in
also
order
difficult. It's also difficult, you're right. But
so we should just do
it's easier.
Mhm.
It's the integral is actually easier. Let's do it, see how it goes.
Wait, so it's a shell method respect to dy or dx?
We'll see. Well, it depends on the picture. It depends on
Oh,
the picture.
okay.
I'll show you in a second. So again, volume when R is revolved around y equal to, what was it, -1. So now we're going to use shell method. Yeah. So how does the shell method work? You're going to take to create shells when this goes around y equal to -1. Again, always draw the region, always draw the axis of revolution like that. Okay. So how are shells created? Just try things out. If you don't see it ahead of time, if you don't see what's what, or what happens when you do what, just try things out. Just do trial error, and it takes seconds. If I were to take a vertical strip, that would be dx. If I take a vertical strip, revolve that around, that's a shell. I'm sorry, that's a washer. Obvious. It's obvious. Okay? You don't need to memorize when, what. Don't do that. Don't do when, what. Don't. You're never going to learn anything if you write down when to do what. Just do it. So that's what's going to happen if you take vertical strips. If I take a horizontal strip like that, revolve that around this horizontal axis y equal to -1, that creates a shell, right? This going around like that. That's your shell. Obvious, hopefully. Okay? So what is the thing about taking a horizontal strip? This has its bads and its goods. The good thing about taking a horizontal strip is that the height, the length, height, whatever you want to call it, the height of the shell or the length of the strip is always gonna be consistent, okay? Right is always blue and left is always green. Always, we have that nice consistency, whereas here we didn't. If I were to take vertical strips, I don't have consistency. The boundaries change. You have to do two integrals, but again, horizontal strip, right is blue, left is green, always, throughout the region. That's the good. The bad is that when you do a horizontal strip, integration is not going to be with respect to x. It'll be with respect to y because this is a dy. Okay? And also, you could see that because in order to find the length of the strip, you have to do the right x minus the left x. So these equations have to be solved for x. They have to. So here it goes. Take a horizontal strip. To find the length of the horizontal strip, which is again, this length is the height of the shell. We need to express, or we need to solve each relation for x. We have to, because of the horizontal segment. Okay. So let me draw the shell and then we'll do that. Again, you can just draw half shell. You don't need to draw the full shell. Half shell will do. Okay. All right, so let's solve each equation for x. Our equations are y equal to square root of 3 minus x. Solve this for x in terms of y. You need to square to get rid of the square root. You have y squared equal to 3 minus x. And then move the x over and solve for x. You're going to get x equal to, I'm going to move this x to the left so that it becomes positive, and move this y squared over to the right. So you get 3 minus y squared. That's the equation of that half parabola, x equal to 3 minus y squared. Okay. I also need to solve this line for x. Our line's equation is y equal to x minus 1. Solve this for x. You get x equal to y plus 1. There we go. And this solves a big portion of the problem. It really does. Okay, so what you want to do is now draw the shell out. Here is that shell. Again, I'm not a very artistic person. I'm just drawing half of it, not drawing the full thing. You can draw the full thing if you want. Draw the full thing. That's fine with me. Here, well, you know what, whatever. Let's just draw the full thing. There we go. Okay, so what you do is locate the center, like always. Okay, center here is y equal to -1. That's what it is. Also, these points. This point is, it's an x, right? This point is on the green line. So that point is described by x equal to y plus 1. And this point is on the blue graph where x is equal to 3 minus y squared. Okay, so you can easily get the height of the shell, right? I want to find the height. This height right here. What do I do to find that length? This length here, guys.
Right minus left.
Do what?
Right minus left.
Right minus left. Right, the right x, the bigger x, minus the smaller x. Okay, and again, these are all in terms of y because of that dy. Just do 3 minus y squared minus the left x, which is y plus 1. Everything has to be in terms of y, guys. So there we have it. We have the height of the shell, and let me write that in pink. The height of the shell is going to be, let me write it in descending order, negative y squared minus y. I'm adding y terms. I have that negative y squared, I have the minus y, and I have a 3 minus 1, which is positive 2. Okay, so that gave us just that length, the length of the strip or the height of the shell. Okay, so we need that. We need the height for the shell. I also need the radius of the shell. The radius is always the tricky part. It was the tricky part for me back in college. I mean, I always had a hard time understanding the radius. But this is the radius of the shell. And the radius is just a y value, right? The distance from here to here is just the y value. So how do we calculate this distance? You could just look at it, get it by looking at the picture. Guys, we know that this distance is 1. This is definitely 1. And this distance is y. This is a y. This is a 1. So the radius is y plus 1. Okay? Any vertical distance is described by y. Yeah, so again, the y coordinate of this point is just y, so you get y plus 1. So again, if you're wondering why this is a y, it's because the coordinates of this point, the coordinates of these this point is, for x is 3 minus y squared. That goes for x, and for y it's just y. Okay, so the y coordinate is y, and then you do minus negative 1, that gives you y plus 1. If your shell is sitting horizontally like that, the distance would be x. But here, because it's sitting vertically, it's a y. One more time, you could see that from this picture. This is y. The distance from the x-axis to any point on the graph, that's a y. And then you have this extra 1, y plus 1. That's our radius. Okay, so we finally have an integral for the volume using cylindrical shells. It's 2 pi times the radius, which is y plus 1. Again, 2 pi radius gives you the circumference, and then multiply that by the height. The height is negative y squared minus y plus 2. Okay, times by the thickness, which is dy. And I need to make sure that I set up my limits correctly. These look at these strips. These strips begin at 0, and they just range all the way through wherever this point is, and that point is at 1. Our y values throughout the region go from 0 to 1. And go to y equal to 1 throughout the region. Okay, Yeah, I admit it might be a bit challenging, and I wish you guys had more time to practice. I really wish so. And problems don't, I mean, problems are like this in the book. I wish I could rewrite the book and make it easier, but I can't.
Is that a negative y cubed?
Say what, buddy?
I think that's a negative y cube, right?
Which one? This one? This?
Yeah.
Y cubed. Why would it be a y cubed though? You have,
Because I thought you had 3 minus y squared on the left, or what is that right there?
so to get this thing, you take the blue minus the green. Just add like terms. This negative y squared, it doesn't have any other like term, right? So I can't add this to anything. Therefore, we have that negative y squared. And then,
Oh, I thought we were multiplying. My
well,
fault.
we are subtracting. We never multiply here because,
I know. That's why I got confused. I'm like, what's going on?
yeah, but to find distance between 2 points, you always subtract coordinates. Always. Yeah, so what I'm gonna do is I will post the problems, and then when I set up that practice session tomorrow, I will go over them with you guys. The solutions are already on there, but do your best to just set up the integral. Guys, it seems like I'm asking too much here, but I'm not. Other teachers will ask you to solve these integrals. They do, and they ask you to do it both ways to check your answer. Do the problem this way and do the problem this way. You have to solve both of these integrals to see if the answers match up. Other teachers, I promise you, they ask you to evaluate the actual integrals. I'm not asking you. And I know it seems like as if there's so much information, but always begin with a simple problem, progress to more difficult ones. Okay, so for instance, if I were you, I would redo this problem revolving this region around y equal to 0 instead of y equal to -1, and see how it makes a difference. Okay, but again, this distance is y. This is 1. That's why we got a y plus 1 as a radius. Okay, yeah.
The way you determined that the integral goes from 0 to 1 is based on the width or based on the radius?
Based on the point of intersection.
Oh, okay,
Yeah.
where it intersects.
Yeah. And that point was at 2, 1 point of intersection that we found. So since the y value here is, this is like the boundary point, since it's a 1, then those strips, they end at a y1. These strips don't go beyond beyond 1.
Okay.
Yeah, so just always ask yourself, if I were to draw horizontal strips or strips like that, where do those strips begin? Where do they end? I can draw my strip, one right here. I can draw another right here, draw here, stack them up all the way to 1. So it goes from 0 to 1.
Okay, and then we only have to like integrate half of it because we're multiplying by 2.
Integrate y half of it.
Well, it wouldn't be like integration from -1 to 1. Because doesn't it? Well, I don't know if I'm thinking about this correctly, but
No, it's not. So your solids from -1, you set -1 to 1. No, because as this goes around, right? As that goes around, you're getting the volume, the full volume of the cylindrical shell.
Okay, so if
Yeah.
it was, so it would be the same answer if you, instead of doing 2 pi, you did just pi times, but you could do integral from -1 to 1, because in that case you'd be doing,
No,
that wouldn't
no,
work.
it's not. It wouldn't work.
Okay,
It wouldn't work because if you do integral from -1 to 1, then you're saying that there are strips here and here and here and here. Those strips range from 0 to 1. You're
yeah, I see.
yeah, you're just finding like a volume of everything in between too, you know. There is a hole, there is a massive hole, emptiness here. We are not finding volume, there is a hole.
Gotcha.
Yeah, -1 to 1, that would be awkward. I don't even know what that region. So if I were to evaluate from -1 to 1, I mean, this graph doesn't go below, so let's see, what would the region look like? I couldn't even create a region because this graph doesn't continue, but like imagine it does. This would be the region. So when you revolve this triangle around y equal to -1, it would give you, what is that, like a dreidel for Hanukkah? Those things that you spin?
Yeah.
Riddle?
Yeah, yeah. What are those things that you spin?
It's a dreidel for sure.
Dreidel, right, dreidel. Right, so. Next topic is also volume, but it's definitely easier, okay? And I'm not gonna go crazy with the next topic. So this is called volume by cross sections.
Professor,
Yeah.
real quick syllabus question. For 5-4, it doesn't have any homework attached with it, and it's just labeled as work.
Hold on.
What does that mean?
Let me see what's 5-4 is. Let me get my syllabus. So yeah, because I am, although I'm talking about this section, I am not going to put it on the test. That's why I didn't put homework for it. I'm not gonna test you guys on work and on this either.
So 8.1 is really going to be the last thing that we go over today.
much.
And okay.
Well, today I have just a few minutes left. So I have to do 8.1 tomorrow, and I'm gonna talk about these, but I will not put them on the test.
So 8.1 is the last section.
Yeah, and 8.1 is the easiest, I think, of all sections.
Is the final during our normal class hours?
Yes, it is.
Okay.
Yeah, there is one more thing in chapter 5.2, I believe. It's volume by cross sections. Yeah, and I think that this topic should have been a separate section on its own, because it's not. It doesn't have anything to do with volume of revolution. So this is just called volume by cross section. And the idea is fairly simple. Okay, this has got to do with a solid in general, a solid that's not really a solid of revolution. It doesn't have to be anything that you revolve, because remember, when you revolve a curve around an axis, it will create either disks, washers, or shells. Pi is always involved. Pi, because of that revolution. All of the volume formulas have a pi, 2 pi, pi r squared. But what if you're not revolving? a solid around anything. Okay, so the way this works out is that imagine you have a, we have a solid here. And so this is a solid, and let's say that the base of the solid is on the XY plane. Okay, so this base is sitting in the XY plane. So imagine this is the, let me do that again. I think I could do this in 4 minutes. Okay, so this is, imagine the x-axis, and this is the y-axis. Okay, but in any case, the base is sitting in the plane like that. And question is, how do we find the volume of the solid? Well, what you do is just cross section. Just take pieces of it. Take a knife, basically, and cut through. Take a slice out. So imagine I cut through like that, and I take a slice out. You know what I mean? Like just a loaf of bread. You have a loaf of bread, just cut, take a piece out. How do you find the volume of this whatever weird looking solid that I drew? Well, what you do is you can cut out pieces, cut out each piece, and basically find the volume of each of those pieces. Okay, and you have all these pieces stacked up, right? You could just cut the solid into many pieces, find the volume of each piece, add them up, doing a Riemann sum or integral. That gives you the total volume of this thing. Okay, so since this thing is an increment of the x-axis, look at that. This increment, this thickness is parallel to the x-axis, then this is a dx, delta x, right? So if you want to find the volume of that cross section, finding the volume of this thing, you're gonna take delta x dx multiplied by the area of the surface times it by the area of the surface. And this is just A. Okay, so here dv is equal to A times dx. You guys believe that? Area of the surface times the thickness gives you the volume of this slice. And we want to find a way to express this area here as a function of x. Why is that? That's because for different x values, we're going to get different cross sections. We do. Not all of these slices are going to have the same volume. Not all of them will have the same area, right? For every x, you might end up with a piece of a different size. So area here depends on x. Okay, if you could express this area as a function of x, that would be great. And then let's say this is A and this is B. To find the volume, we just do the integral from A to B. of a of x dx. Add up the volume of all slices. So I'll do a couple of examples tomorrow. To be honest with you, tomorrow is not a long day. It's not. Section on the arc length should take me, this section should take me maybe 20 minutes to cover arc length. And I'm gonna take like 10 minutes to talk about work so you're aware of it. And maybe 10 minutes to talk about 6.1. But 6.1 will be done in Math 8. I don't know why this section is still in Math 7. And yeah, I'll do a couple more problems from volume and then cover that, talk about these. And then I'll be holding a practice session tomorrow for sure. Okay. But yeah, that's it for today.
I know you mentioned like trying to find a study guide for us. That something that you will be sending like today or tomorrow?
Hold on.